Good morning, good afternoon, good evening, wherever you are in the world, and welcome to the IconX talk. And today is Friday, and then Friday is the day for the IconX talks. And the purpose of the IconX talks is to connect the world and the universe, and promoting science and scientists, and really connecting the people through science. And that's the main purpose of IconX talks. And today we've got a very distinguished speaker, Professor Carmen Menoni from Colorado State University. And also we've got our challenger, Dr. Jing Tang from Stanford University. And our panelist is Professor Alice Zhang from Peking University. My name is Jagadish, and I'm from the Australian National University. And so really I'll be serving as a moderator for this today's talk. And it's my pleasure and honor for me to introduce Professor Carmen Menoni, my dear friend and a distinguished colleague for many years. And Professor Menoni has done pioneering work in the field of photonics, and then she is the University Distinguished Professor at the Colorado State University, and is in the electrical and computer engineering, as well as honorary appointments in chemistry, biomedical engineering, and also applied chemistry for drug discovery departments at the Colorado State University. She has done outstanding work in many areas, and so particularly in the area of amorphous oxides for developing coatings which are used in LIGO, for example, in discovering the gravitational waves. And also she has been very actively involved in the development of the XUV lasers, and then using the XUV lasers for the lithography applications also. In fact, she's a co-founder of the XUV lasers company, and she has won many awards and recognitions, and so she's a fellow of IEEE, and OSA, SPAE, American Association for Advancement of Science, American Physical Society, and also currently she's serving as the president of the IEEE Photonics Society. She was also founding editor-in-chief of the IEEE Photonics Journal, and success of the Photonics Journal has been mainly due to the energy and passion put by Professor Menoni. Today, Professor Menoni is going to share with us an exciting developments in the field of amorphous oxides, and how they are useful for the photonics applications. And please join me warmly welcome Professor Menoni to this today's IconX talk. Professor Menoni, please go ahead and then share your talk, please.
Thank you, Jagadish, for the introduction, and thank you for the opportunity to share our work on amorphous oxides for photonics applications. So amorphous oxides have played a paramount role in technology.
Carmen, sorry,
yes?
Yeah, that's a double screen here.
Yes, so maybe you get into the, I think people can see your notes as well. So yeah, that's good. That's good.
Yes.
Carmen, that looks good now.
Is it good?
Yeah, it's
okay.
Good.
Let me do, yes, I know it's my computer that goes into this mode.
Okay, thank you. No, it's gone again.
Okay. I have to, I'm sorry. Okay, I have to share again a screen. Thank you very much for the opportunity to present our work on amorphous oxides for photonics application. The amorphous oxides have played a dominant role in modern technology. For example, silicon dioxide forms the backbone of optical fibers that are actually communicating the world, and is in a certain sense making possible this presentation. Amorphous oxide, and in particular silicon dioxide or silica, is also used as a high-K dielectric in the most advanced semiconductor chips. Superb control of the material's properties has been instrumental in achieving a state-of-the-art performance. Thin film metal oxides are also used in photonics technologies. And in this particular case, as I showed here, for example, these photonics application exploit the index contrast between the amorphous oxide and air in this case of the grating that is used in nanophotonic circuits for integrated quantum technologies, or in the case of this waveguide that was designed to confine light. The reason why amorphous oxides are unique for photonics applications is that they have a very large bandgap, and therefore they are transparent in the wavelength range between 0.3 to 2 microns. In addition, they offer a large index contrast, and this is critical for photonics application. We can also deposit materials in thin film form that will have extremely low absorption loss. Our application is to use the amorphous thin film oxides to engineer multi-layer dielectric coatings. These dielectric coatings are stacks of 2 alternating layers of amorphous oxides, one that will have a high index, like for example, hafnium dioxide or hafnia, and the other one a low index, which like for example, silicon dioxide or silica. By tailoring the layer thickness and knowing the index of refraction, we can actually obtain or design a desired optical response. This technology is ubiquitous in any optical system. However, in the applications that I am going to describe, they offer challenges. And those are the challenges that we are trying to overcome by both studying the materials and optimizing the structures. And the two efforts that we are focusing right now, in which we are trying to achieve performance in multi-layer dielectric coatings beyond state of the art, are in interference coatings for ultra-high intensity near-infrared lasers and for ultra-stable laser cavities of gravitational wave interferometers. So this is the outline of my talk. After an introduction on amorphous materials, I will move on to discussing the problems that we are trying to solve to design interference coatings for ultra-high intensity lasers that are robust to withstand the energies and repetition rate of these lasers. And then I will describe the materials problem that we are trying to address to engineer the next generation of interference coatings for gravitational wave detectors. So amorphous materials, unlike their crystalline counterparts, do not lack long-range order. However, they do have order at short range, which is defined as length scales of about 5 angstroms, and medium range, which is defined in the length scales of about 20 angstroms. So in the short range, amorphous oxides, and I show the case here of silicon dioxide, are arranged in the form of polyhedra. And this is a tetrahedron in the case of silicon dioxide that mainly in which silicon is mainly covalently bound to oxygen. In the medium range, the structure of this oxides form is in the forms of rings. And you will hear throughout this talk that I will refer to this ring formation. And what you are seeing here is the picture of the tetrahedron just seen from in 2 dimensions that are connecting each other. So nature makes amorphous oxides by cooling very, very slowly. And And so we have a super cool liquid that essentially at a given temperature becomes so viscous that then and solidifies. And this is what we call the glass. Nature has been fantastic in actually making also beautiful crystals by this is actually the equilibrium state, and this is which is what we are used to seeing in many different art forms, and that is quartz. Quartz is actually the second most common mineral in the earth crust. In the lab, we make amorphous oxides by vapor deposition. The high K dielectrics in semiconductors and the fibers are made by chemical vapor deposition, which is a high temperature process. Instead, thin film oxides that we are using and that others are also using are made by the physical vapor deposition. This is a cartoon of one of the deposition systems that we use to make thin films. This process is termed ion beam sputtering because we use a gridded ion source to actually create an argon beam, an energetic argon beam that actually sputters either a metal or an oxide target, creating a plume of vapor that consists of molecules, atoms, and clusters that then deposits on a substrate that is rotating for uniformity purposes. This process offers a lot of flexibility in the selection of the material that we need to grow because it depends only on selecting the target. And we can make binary oxides, we can also make mixtures. In addition, it offers Armstrong precision in layer thickness. And so we can grow nanolaminates in which each of these layers is a few nanometers thick. This is the case of tantala or tantalum pentoxide and silica. Or we can also grow multi-layers with superb interfaces. And this is very important to tailor their optical response. Now, the materials that we grow by ion beam sputtering are amorphous, but their structure is complex because the process, this is a low temperature process, and therefore, when these particles, atoms, molecules land on the substrate, they have very little mobility. So depending on the deposition conditions, sometimes one can form these columnar growth. This is not very common in ion beam sputtering, but yes, sometimes in electron beam evaporation. In the short and medium range, again, the materials consist of these connecting polyhedra. And there is, in addition, a network of oxygen defects in the form of interstitials and vacancies. We can, to a certain extent, modify the structure because in our system, we have an assist source that is directed towards the growing film. So we actually sometimes use it for specifically to modify microstructure and reduce stress to bombard the film during growth. So the materials that are synthesized are amorphous. As you can see here from this X-ray diffraction spectrum of tantala, that there are broad peaks. Here, these lines, these arrows indicate where the peaks of the crystalline orthorhombic tantala should be. Macroscopically, they are also stoichiometric, as shown by these spectra, these X-ray photoelectron spectra. And they are very uniform, as shown by this transmission electron microscope image. Now, for our purpose, we need to characterize very well their optical properties. And so we do a spectroscopy ellipsometry to obtain the dispersion of the refractive index and the extinction coefficient. And we do very sensitive absorption measurements. We use photothermal techniques like photothermal common path interferometry, which was developed by our collaborators at Stanford and has a sensitivity below 1 parts per million. We have also, in collaboration with the University of Buenos Aires, developed a technique, a photothermal technique that can map absorbance also with a high sensitivity in the parts per million and a pixel scale of about 3 microns. Now, as I mentioned, the growth process it occurs at low temperature. The particles or the deposited material sticks where it lands. So and furthermore, the particles do have an energy when they arrive to the substrate. As a result of that, the films have very high compressive stress. So the way that we assess the stress in the thin films is by interferometry. We measure the deformation of the wavefront of the substrate, as I show here, in which we coat single layers or multi-layer. And then we use the Stoney equation to relate wavefront deformation to stress. Just to give you numbers, the compressive stress in tantalum pentoxide is of the order of 140 megapascal. In silicon dioxide is 400 megapascals. And so in recent years, we have been actively investigating how we can use the process to reduce stress. And actually, by bombarding the film during growth with the assist source operating with an oxygen beam, ion beam, we can reduce stress in silica by about a factor of 4 compared to the regular silica that we deposit. And in this particular case, we use an oxide target. So as I mentioned, we can also grow mixtures. And what mixtures do is they alter the optical and structural properties of the oxides. So for example, I showed the example here of 2 mixtures, one of silicon dioxide and tantalum pentoxide, and the other one of titanium dioxide and tantalum pentoxide, with a cation ratio of about 20%. So adding silicon dioxide to tantala, silica has a lower refractive index, so the mixtures will actually have a lower refractive index than pure tantala. But at the structural level, there are also some interesting modifications. For example, if we take these mixtures and we anneal them to the level of crystallization, we have observed that in some cases we observe phase separation. For example, in the silica tantala mixture, we observe that tantala crystallizes, although at much higher temperatures than pure tantala. But whenever we add titanium to the mixture, what we observe is that after we crystallize the material, there is the ternary phase formation. And this is going to play a very important role in the organization at medium and at medium range that is critical for coatings for LIGO. We have recently shown that it is possible to predict the behavior of the oxides actually using data for crystalline materials. Mariana Facio, one of my postdocs in the group, actually did show that we can use the results of the materials project database to calculate phase diagrams, and also in combination with oxygen ground potential diagrams to predict whether we will have ternary phase formation or phase separation in the mixture. So to design interference coatings, we select a high refractive index material and a low refractive index material. And by knowing the refractive index as a function of wavelength, then we can tailor the layer thickness to obtain the desired composition, the desired optical response. And I show here a reflectance curve for a mirror that consists of 32 pairs of hafnium dioxide or hafnium and silicon dioxide or silica. What I want to point out also is that when this coating is illuminating, there is an electric field distribution that is shown here in this plot that is oscillating. But what I want to highlight is that the peaks of these intensity standing wave electric field that is created in the coating is actually in a quarter wave structure peaks at the interface where we deposit the hafnium layer on top of the silica layer. And these will become important to actually modify when we design coatings for ultra-high power lasers. A typical absorption loss in a reflector at around 1 micron is 30 parts per million as deposited, and we can lower it to about 10 parts per million with annealing. Typical stress is 400 megapascal. The stress is also reduced when we anneal. You can see an interferogram of that shows the stress in this particular coating here. So it is possible to grow multi-layer dielectric coatings with absorption loss of less than a part per million. And this is actually, these outstanding results have been obtained in the multi-layer structures that are used in the present LIGO coatings. So when we design interference coatings, there are many aspects that we need to look for. If we are designing interference coatings for continuous wave, high average power lasers, this will be the case of LIGO, then we are going to require that the coating has very, very low absorption of a few parts per million. And this is because impurities and defects cause local temperature increases that when they reach a sufficiently high temperature can lead to melting, boiling, fracturing of the amorphous layers. So the typical material that is used as high index is tantalum pentoxide, and the low refractive index is silicon dioxide. As I am going to describe for LIGO coatings, we are also require that they will have low internal friction. Instead, when we design interference coatings for high energy picosecond and femtosecond lasers, we will use the materials that have the largest bandgap. And this is because nonlinear absorption, multiphoton, and avalanche ionization and plasma formation dominate in the interaction of ultra-short pulses and the materials. Again, here we are going to strive to have low absorption loss, but it's not required to have ultra-low absorption loss. 10 parts per million is sufficient. We are going to require that the coating has low stress, and also we are going to tailor the position of the peaks in the standing wave electric field to lie in the low index material that is the most robust to laser damage. Now, if we go to ultra short pulses, then we also need to take into consideration dispersion control. And that becomes a little bit more challenging because we need to then incorporate in the design multiple, probably 2 materials for as high index layers instead of just 1. So let me now move to describing our efforts in the engineering of optical coatings for high intensity, high energy, and high repetition rate mid-infrared lasers. As you know, shear pulse amplification, this concept that was demonstrated by Don Strickland, Gerard Moreau, and others, has enabled to achieve the shortest possible pulses. Now, when applied to solid-state lasers, shear pulse amplification has also enabled the demonstration of high energy petawatt and multi-terawatt lasers. Now, there are critical components on this shear pulse amplification system that use coatings. For example, the coatings in the laser amplifiers and in the multi-layer dielectric gratings in the compressor. And right now, these coatings are a limiting factor in achieving higher pulse energy and higher repetition rate. So our efforts are combined theory and experiments, and are directed towards improving the performance of the anti-reflection coatings in the amplifier crystals and other critical components for two particular lasers that are being developed at Colorado State University by Jorge Roca and colleagues. And these are one terbium jack shear pulse amplification laser that has achieved record performance, 1 joule, 1 kilohertz, 5 picosecond pulse duration, and a petawatt class laser based on titanium sapphire. And so here the materials that we use for coatings are hafnium dioxide and silicon dioxide. And what we are looking at is reducing stress. We are also developing strategies to condition substrates. We are looking at the role of interfaces, and we are also looking at new materials. And as I mentioned, we collaborate with Inan Chowdhury of Ohio State University and Vitaly Grufer from University of New Mexico, who are actually modeling the laser-matter interaction and giving us feedback on how we have to tailor the material properties to increase the robustness of these materials to laser damage. So one of the examples of the work that we have done is we have investigated the performance of anti-reflection coatings and high reflectance coatings in Arctic mirror amplifiers for the ytterbium jack. And here what we learned is actually that we not only have to make good coatings, but we also have to condition the interface between the coating and the crystal, because at the interface there are defects that actually will intensify the electric field and cause damage. In another study, we investigated the mechanisms that give rise to damage in these coatings at ultra short pulse. These are single cycle pulses of duration of 8 femtoseconds. And what we learned from these time resolved images is that prior to damage, there is actually a blister formation that is reversible with fluence, and that occurs at the interface between the first hafnium layer that is deposited below the top silica layer. And so these results suggest that, again, interfaces are very important, and also stress is very important. And so we are addressing those issues by modifying the materials. So there is intense activity worldwide in developing multi-terawatts and petawatts lasers. And therefore, our work will contribute to these developments by enabling actually much higher energy extraction out of the solid state amplifiers, and through the improvement in the laser damage performance of the coatings. Furthermore, if we make more robust coatings, the size of these lasers could also be reduced. These lasers, these high intensity, high repetition rate lasers, are envisioned for applications like these laser-driven particle accelerators, intense X-ray source generation, and relativistic laser-matter interactions. Along these lines, we have used these lasers for some applications. Jorge Roca at Colorado State University has used the lasers to investigate relativistic laser-matter interactions, and have shown that when these intense lasers interact with nanowire arrays, it is possible to produce high-density plasmas, with a density that is densities and pressures that are similar to that of stars, and therefore these dense plasmas are intense sources of X-rays if metal nanowires are used, or neutrons if plastic nanowires are used. We have also used the lasers to demonstrate tabletop soft X-ray lasers that emit at wavelengths down to 6 nanometers. And these are very bright sources as well, producing microjoule energy pulses that we have actually used in applications like single shot and time-resolved microscopy and holography, defect-free lithography, and 3D nanoscale chemical and isotopic imaging. Let me now move to our efforts in understanding the materials problems that are prevalent in interference coatings for gravitational wave interferometers. Gravitational wave interferometers are kilometer-long interferometers, and in the mirrors in the end-test masses are coated today with amorphous thin film oxides. When a gravitational wave comes in, it causes expansion and dilation of the arms of the interferometers, creating an interference signal. The sensitivity that these interferometers have is outstanding. They need to measure distances in changes in distances that are of the order of 10 to the minus 21 per root hertz. Just to give you an idea, these are length scales that are about 1,000 times smaller than a nucleus. So using these interferometers, since the first detection in 2017, we have been seeing that the LIGO and Virgo activity, LIGO comprises 2 interferometers here in the US and Virgo 1 interferometer in Europe, has been extensive in showing us essentially the merger of black holes and the merger of also binary nuclear stars. So recently, LIGO and Virgo detected the most massive merger of 2 black holes that gave rise to a black hole that has a mass that is 140 times that the mass of the sun. Now, as you're aware, as I said, there are numerous technologies, that go into realizing this level of stability and sensitivity that this interferometer has. And this plot here shows all of the sources of noise in strain noise as a function of frequency that of the interferometer, of the advanced LIGO interferometer. And if you see here, the purple line and the red line are the limiting sources right now, and they correspond to quantum noise that is being addressed by using a squeeze light and coating, Brownian, or thermal noise. And this is the problem that we are trying to address. So coating and thermal noise arises from the thermally activated motion in the coating that leads to elastic energy loss. it couples into the detected signal and therefore produces noise, adds noise to the detected signal. Thermal noise is proportional to the mechanical loss angle, and this I will be referring to this measurement throughout my talk. This is a picture of the end-test mass of the LIGO interferometer. This is the substrate is fused silica, is about 30 centimeters in diameter, and is about 30 centimeters long. And what you see here is the reflection of the coating of the oxide coating. So in the present the present interferometers that are called advanced LIGO, the interference coatings consist of a stack of silicon dioxide and titanium dot tantalum. In this pair, it is the high index layer that actually has the highest mechanical loss. Silica has about a factor of 10 lower mechanical loss. So all of the efforts have been devoted to understanding the origin of mechanical loss and reducing it. And so there is a roadmap for the development of coatings for next generation gravitational wave detectors. And advanced LIGO Plus is actually requiring that the coatings had 2 to 4x lower mechanical loss, which will translate in a factor of 2 lower thermal or Brownian noise. So a way to understand what is mechanical loss angle is just to think that if we have an oscillating strain, we can have a lag between a stress and a strain, and that lag is actually is known as the mechanical loss, which is indicated by the angle phi, or also q to the -1. So the larger the mechanical loss, the larger the elastic energy dissipation. Now here I show the power spectral distribution of Brownian noise, and this is a measurement in the mirror, and so you see that the Brownian noise of the mirror is proportional to the mechanical loss of the coating. It's also proportional to the thickness, the total thickness, and proportion dependence also on the Young modulus of the coatings. So how do we measure mechanical loss? Actually, we don't, but this is done by our colleague Gabriele Vagente at LIGO Caltech. He uses this cavity ring down technique in which the different modes are excited in a sample that consists of a few silica substrate of 10 centimeters in diameter, 1 millimeter thick, where we deposit the coatings. So he excites with his the different distortion modes in these samples, and then measure the decay signal, the ring down signal, and from there extract the mechanical loss angle. But what is the origin of mechanical loss? Well, to understand the origin, we have to actually rely on models. In a simple way, we can think that if this is, the tetrahedron, for example, silica connected to oxygen atoms here, there will be instabilities in the bonding, and these instabilities in the bondings actually give rise to mechanical loss. So these structural modifications are modeled as two-level systems, as I show here. And so the model shows that transitions, different organization or different connections of the polyhedra can be associated with different wells. And in these two well picture, and so transitions will occur, transitions between the different states are represented here as different organizations of the tetrahedra. Transitions below 5K are assisted by tunneling, and above 5K, which are the ones that we care, are thermally activated. Now, recently, our colleagues at the University of Florida have shown with model simulations that in zirconia tantala, there are two types of bonding instabilities or structural instabilities that occur at the medium range. And those are labeled cage breaking and non-cage breaking transitions. Cage breaking transitions involve, for example, the breaking this bond and restructuring of the polyhedra to form larger rings. These type of transitions in the potential energy landscape corresponds to transitions that have actually large barrier heights. Non-cage breaking transitions correspond, for example, to the polyhedron rotating around a connection. These are predominantly the type of transitions that occur in cryogenic loss that actually is detrimental in affecting coherence in superconducting quantum bits. Coupled to this work, Kiran Prasad from Martin Feyer's group at Stanford, in collaboration with us, showed in experiments and simulations that in zirconia tantala, the reduction in mechanical loss is actually associated with an expansion in the polyhedral connection that is schematically shown here. So he, using grazing incident X-ray pair distribution functions and modeling these, showed that there is a decrease in the population of phase share and edge share in polyhedra, and an increase in corner share polyhedra when the amorphous oxides are annealed to below the crystallization temperature. So we have conducted extensive studies on mixtures, and in particular, the one that is used in the present LIGO coatings. And to this picture of reorganization, what our studies have added is that for a specific content in the titania dope tantala of about 27%, when the alloy is annealed, there is a reorganization that takes place that actually is reflected at the crystallization stage by the formation of a ternary phase whenever the concentration is 20%, or by the instead, when the concentration is higher, we see that only titania crystallizes in rutile 4. What mechanical loss measurements revealed is that actually the mechanical loss of the dope samples is lower than that of tantala, but the alloy or the mixture that achieves the lowest mechanical loss is the one that contains 27% titanium content. And this result is consistent with what has previously been measured in titania dope tantala. Just to give you an idea, the optical quality of these mixtures is excellent. We measured 4 parts per million absorption loss in the 27% titania sample at 600 degrees C annealing. So motivated by these results, we investigated the doping of tantala with other oxides and at about approximately 20% cation ratio. And what we learned is that most dopants will increase the thermal stability of tantala, but only in the case in which we dope tantala with titania or zinc oxide is when we observe ternary phase formation. And again, all of these, the evolution of the films with the different dopants can be predicted by density functional theory models from the materials project database. So what about mechanical loss? Well, again, this plot shows loss angle as a function of dopant, and the results are plotted at the highest temperature at which we anneal, and the material will have the lowest mechanical loss before, and this is the highest temperature before crystallization. So what we see is that all of the dopants decrease mechanical loss, but the decrease is most significant whenever we form a ternary compound. And again, this corresponds to an organization in which we optimize we will likely optimize, as is the case of titania doped with zirconia, these corner shell structures, and also in addition, when this happens, the dangling bonds, oxygen dangling bonds, are reduced. Now, there are other strategies that are being investigated to reduce mechanical loss in amorphous oxides, and making nanolaminates is one of them. And so I show here transmission electron microscope images of nanolaminates that we made with tantala and titania and tantala and silica. And what we showed in this work is actually when we anneal these nanolaminates, the silica nanolaminate, the silica tantala nanolaminate remains intact, but the titania tantala nanolaminate instead, with the interfaces break, and showing that there is diffusion of tantala and titania. Interestingly, the tantala titania nanolaminate is the one that achieves the lowest mechanical loss, and it achieves a value that is very consistent to that of the mixture, as can be seen here. These are the results of the mixture and compared with the nanolaminate. So what these results showed us is that that actually the diffusion that occurs is predominant in the titania doped tantala is actually what drives the reduction in mechanical loss. And what I show here is that we have also observed this diffusion through X-ray photoelectron spectroscopy measurements that shows that the titanium environment significantly changes. Instead, in the silica tantala nanolaminate, we see no cation diffusion. So models show that actually for titania doped tantala, it is the bonding, the titania oxygen tantala bonding, and that is important in obtaining a high degree of structural homogeneity at the medium range, and again through these polyhedral connections, and that reduces mechanical loss. Now, in search for new alloys, we also investigated other binary oxides, and here I plot the loss angle for a family of binary oxides that are arranged according to their coordination. And for example, their tantala falls within the group of modified continuous random network, and it has a mechanical loss of about 5×10⁻⁴. The next group includes yttria, zirconia, and hafnia, is identified as random closed pack. And then the group that has the lowest mechanical loss are the continuous random network, and it includes silica and germania. So we evaluated the possibility of designing coatings with hafnia and zirconia. But if you look at this table, the Young modulus of zirconia is very large compared to that of silica. And as a result of that, the gains that will be obtained by using a material with lower mechanical loss angle will actually be offset by the differences in the Young modulus which also come into play when we calculate Brownian noise in the coatings. But based on these results, we decided to actually investigate whether Germania would be a good candidate as a base for coatings for the next generation coatings for advanced LIGO Plus. Germania, like silica, is a strong glass former. So it organizes in this tetrahedron and that actually form rings, and I show here a 3-member ring. And these rings actually describe the organization at medium range. So we investigated the evolution in the medium range organization of Germania using Raman spectroscopy. And you see here the Raman spectrum of Germania that was deposited at room temperature, and that was another sample that was deposited near the glass transition temperature at 0.8 TG, which is about 400 degrees C. The spectrum contains 2 peaks that are identified here as the red peak corresponding to 6-member rings, and the green peak that corresponds to 3-member rings as shown here. 6-member rings are stable in the crystalline structure. So we used the ratio of the areas of these 2 peaks as a measure of the changes in medium range order. And we investigate, here I plot the ratio of the areas of the 6-member ring to 3-member ring as a function of annealing temperature for the 2 samples that were deposited at different temperatures. And what you see here is that indeed growing at high temperature has a much higher degree of ordering, is the more relaxed structure. So how does this translate into, relates to mechanical loss? Well, the higher increase in medium range order actually leads to a decrease in mechanical loss. So motivated by these results, we are now doping Germania with different dopants. The reason is that Germania has a refractive index of 1.6, so it does not offer significant contrast with respect to silica. And of these 2 alloys, the ones that seems to be more promising and that is actually titania doped Germania. So our goal is now to work on this alloy to obtain an alloy that will have 4x lower mechanical loss for the next generation of LIGO coatings. So essentially what I showed you is that by crafting the materials, understanding the fundamentals of the materials, we can actually tailor their properties, in this case, this structural rearrangement at medium range to obtain a mechanical loss. And we have different tools at hand. We can change the materials properties by changing the position conditions or also by making mixtures and nanolaminates. With that, we hope to get to demonstrate these new coatings that will allow LIGO to actually reach further out and look at the collision of larger black holes or binary neutron stars and collisions that occur much farther away, opening up again, answering new questions on the origin of the universe. So this is my last slide. I would like to thank my group, shown here, for all of their contributions to the work that I just showed. I would like to thank the collaborators that are listed here, both in the efforts of interference coatings for high energy lasers and also the interference coatings for gravitational wave interferometers. And I would also like to acknowledge the support of the funding energy agencies, and also would like to thank you for your attention.
Thank you, Carmen, for this wonderful talk, and then really exciting developments, and then these amorphous oxides and how they are contributing to a wide variety of technologies, and in particular to LIGO, and then how that's impacting allow us to be able to do exciting the astronomy, gravitational wave astronomy, and particularly discovering of wide variety of unexpected and the discoveries taking place. So we've received many questions, but because of the time limitations, and what we do is that we end up restricting the questions to 3 of them. So the first question is from the wonderful talk, Professor Carmen. And so this is Xinghua Hu from HNU. As you said that the interface defects is very critical, it depends on materials or proper processes.
It's actually both, and so I did not show results, but it is actually interesting that that when we deposit one material, for example, we deposit hafnia on top of silica, is actually not the same in terms of stress than when we deposit silica on top of hafnia. And this tells you that interfaces play a very important role. So, I mean, yes, it could be, this could be altered by process. And we do that specifically with, by changing the energy of the ions that we use to spatter the materials, or using the second assist source in our system that is constantly impinging during material growth. And we can actually change the conditions when we are growing the bulk or when we are growing the interfaces. But this is actually an unexplored area. So we are now getting into looking at interface defects and trying to understand their role and to control them.
Okay, thank you, Carmen. The next question is from Lily from Peking University. Thanks for your excellent talk. And besides the mechanical loss with annealing temperature, does the mechanical loss related to the thickness of the thin film?
The mechanical loss is actually not related to the thickness of the thin film. Just to give you an idea, I mean, we normally grow the thin films that are in which mechanical loss is measured are about 500 nanometers thick, and we do that because this is what our colleague at LIGO needs. I mean, mechanical loss arises from energy dissipation. Now, Brownian noise will depend on thickness, yes. Okay. So that's the reason why when we design the coatings, we want to have this very high index contrast, because that will actually reduce the overall thermal noise or Brownian noise in the coating.
Okay, thank you.
I want to mention that along these lines, LIGO and Virgo are also looking into using crystalline coatings made of gallium arsenide algas quantum wells. Okay,
good. Okay, thank you. So that's a question which I have, is that I understand the next stage of LIGO will be operating at 2-micron wavelength, and what are the challenges in creating coatings at this wavelength?
Okay, so yes, I mean so the next stage is advanced LIGO and is room temperature. Then there are plans for other gravitational wave detectors that will actually operate at 2 microns, like Cosmic Explorer, and will also operate at cryogenic temperatures. Well, the challenge here is that we don't know much about the response. We know, and actually we do have an effort in developing 2-micron wavelength coatings, that we can actually, from the optical standpoint, we can still use the oxides to realize high optical quality, very low absorption loss coatings at 2 microns. However, the mechanical loss properties are different, especially from room temperature to cryogenic temperature. So as a result of that, I mean, this is an unexplored regime, and we are going to start working with our collaborators at the Centers for Coatings Research we are going to start looking into mechanical loss of the oxides at cryogenic temperatures. And I can tell you, there are preliminary results that, there are results on pure silica that show that silica actually will not be suitable as a low index material because it has a peak in the mechanical loss at cryogenic temperatures. So some of the candidates that are being looked at are, for example, amorphous silicon.
Okay. Thank you very much, Carmen, for those exciting talk, and then also answering all the questions very nicely. So now we'll move to the panel discussion, and so then, of course, our panelist is Alice Zhang, and Professor Alice Zhang from Peking University, and then, of course, Alice is famous in all over the world, and by founding the Iconics talks, and then also really promoting science and scientists, and then let us warmly welcome Professor Alice Zhang to the panel.
Hi, everyone. I'm here.
Good. Thank you for joining us, Alice. And then, of course, our challenger today is Dr. Jing Tang from Stanford University. And she is an absolutely rising star. And she did her PhD from Fordham University Chemistry. And she has moved to Harvard and MIT as a postdoctoral fellow, working with some famous scientists like Bob Langer, and who has, in fact, has given last month an Iconics talk on drug discovery, and also Professor David Kohenev at the Harvard University as well, as a joint postdoctoral fellow. And then now she's working as a research fellow in Professor Yi Tsui's group at Stanford University. And she has been recognized as the under 35 technology review, MIT Technology Review in China in 2020. So please join me warmly welcoming our rising star and outstanding young scientist, Dr. Jing Tang, as the challenger.
Hello, everyone. Yeah.
So now
thank you.
Then maybe we'll start with some panel discussion. And so generally we give the opportunity to our challenger, being an young scientist, to ask the first question. Please go ahead, Jim.
Yeah. Thank you, Professor Jagdish, for your kind introduction. Thank you, Carmen, for your great talk. Today, I'm highly honored to be ICANN Talks ex-challenger. I'm excited to learn from the knowledge and experiences of our hosts and guest professors. Carmen, most of my questions are about your career path. I really enjoy hearing women scientists share their story, because I think it inspires and instructs others. My first question then is, looking back at your trajectory, if you could change anything, what would you change? Carmen.
No, that's a very interesting question. And what would I have changed? Perhaps what I would have changed is at the beginning of my career, I did not have the instinct to actually, or the vision to actually identify key, problems. And I think this is very common to all of us after we graduate. When you are doing your PhD, you essentially are very focused on a topic. And it is interesting that, I did my PhD in physics in very fundamental research. I mean, I looked at phase transitions in silicon and germanium under ultra high pressure. When then, I became a professor in the Department of Electrical and Computer Engineering, I realized that that was a very fundamental topic that I needed to adapt, to bring in some more practical or technological focus. And that's when I started to actually squeeze to high pressure devices. We squeeze laser diodes and LED. And that what we learned in there is actually how the materials behave in a similar way, because pressure behaves in a similar way to changing composition. But perhaps at the beginning, I was not sufficiently active and to actually look into very different areas. So that's the reason why it is very important, like in your case, you're doing several postdocs. That is exactly what these experiences give you. Working with different professors, in different groups, in different areas, is very enriching, because when you mature as a researcher, then you can use all this knowledge to actually move into new different fields. And as I look at myself, and I am already now in my 4th postdoc in my professional development, because I started as a semiconductor person, then I moved into into dealing with oxides, and I went also into, as an spectroscopy, I went into the extreme ultraviolet and soft X-ray, which is a region in which there is very little, there is much less done than in the visible regime. So getting experience working with different people is key to actually, crafting your future, your professional future.
Yeah, thank you so much for that, Carmen. I have observed that leaders like yourself in academia are able to manage many different projects, people, and positions effectively. So my next question is, how have you personally developed this leadership skill? What are the key capabilities you have developed to manage at your responsibilities?
Well, again, that's you're sort of, when you, I have all my professional career has developed in academia, and so this is, in a sense, the expectations that you have are what are driving your professional development. But in addition, I am a very good observer, and I learned from my colleagues. I learned a lot from my colleagues. I see how they operate, and I have very good mentors when I joined Colorado State University. I came in the Department of Electrical Engineering into a group of mainly full professors that were very established in their areas, especially in semiconductors. And they really were excellent mentors in that they provided me with the resources to actually carry out my ideas. And then, of course, this is the way you grow and you start building your professional life and activities. But in addition, ever since I was an assistant professor, I worked with the professional societies, and I started working with the IEEE student group here at Colorado State University, being an advisor. Then I moved to the Photonics chapter in Colorado, and of course there I helped organize all the activities and so on, until I became the lead. And then this also brought me to start interacting with the Photonics Society at a much higher level. And of course, that was actually a good learning experience that really taught me about leadership, because I was given tasks, when I was vice president for publication, for example, that at a certain point seemed very risky, and so you have to learn the skills of how to socialize ideas and how to sell ideas and so on. And this is what we do for life, correct, in our profession.
Yeah. Thank you. Thank you so much, Carmen. I feel that it's a great advice for me. So my next question, I'm wondering, how would you recommend a junior colleague find a mentor in their department, what are the junior colleagues' responsibilities and what can they reasonably expect from a mentor?
So finding a mentor is actually sometimes is, you know, by chance, and it doesn't necessarily have to be in your own department, but rather it has to be, you have to find a person that will actually be very honest in giving you advice. And for example, I serve as mentors to young faculty members here that are in other departments, and essentially, you know, in the role of a mentor, I try to highlight what is the metric and how to handle certain situations. Now, for someone younger, you know, that like you, that you are, working in your department, you can find mentors. It could be someone, you know, in your group or someone else in another group. But the most important thing is that to find a mentor, and an effective mentor and mentee relationship is one in which you can openly talk and you can actually explain, you know, what are your concerns and how this could be addressed, or, you know, or ask for feedback on what are the things that you need to do in order to advance to the next stage, or what are the things that you are doing that are not productive. So I think, you know, that this is how it works. I mean, I would say you need to have mentors, but you also need to have supporters to develop professionally. And these supporters are also your family and friends. And this is the ecosystem that you need in order to succeed professionally.
Okay. Yeah, maybe I follow up for questions here. Yeah, actually,
Please go ahead, Alice.
yeah, thank you very much. Actually, you joined the Rose in Science, and then now I invited you to, you know, get on stage of ICANX. Excellent talk. Yeah. So, for this experience, you know, I engaged with you for 2 months or something. I feel that you did everything perfect. You know, yeah, exactly. Every time, you know, PPT, everything, you know, perfect. Your talk, you know, yeah, on time, everything. So, I mean, how you handle all this, make the family work and all these different kind of things perfect and balanced.
Okay,
What's your magic?
What's my magic? Okay, my magic is that I work very hard, and just to give you an idea, I was, you know, practicing this talk yesterday throughout the afternoon to, you know, because I was very concerned with my timing, and also, you know, the concepts, some of the concepts, especially the on the materials issues that we are trying to address in LIGO, are not are concepts that unless you are in the field are not, you don't hear them very frequently. So how do I balance my life? Right now, I am in a stage of my life in which I could say I enjoy the freedom to dedicate long hours to my work and to which is my passion. I have a very strong supporter in the house, that's my spouse, who has always been a supporter. But in addition, you know, throughout the different stages of, you know, professional development, I always secure help. And I secure help from the village. You know, whenever our children were young, I connected with other mothers that will help me, for example, take, you know, the children to different activities. I also, you know, we also had a very special arrangement in which, you know, we had the help of the grandmothers during the time that the children were young. But I use the skills that I use at work, I try to be very efficient and try to optimize absolutely everything. I plan ahead things so that then I know that whenever the time comes, I will be able to handle the activities. But I go through times that is very stressful, especially, whenever we have to submit proposals or when you have to ask, write reports or give presentations. This time now that we are in which we are constantly connected, we assume, to our community, is also, I understand that it's very stressful, and I feel for those who have young children right now, for those scientists that have to take care of young children, because balancing, when you have to when you have to work, when you have to pay attention, and balancing work and family is very, very challenging.
Thank you very much. Yeah, so I really admire you, that everything so perfect.
Well, it appears, okay? We work hard.
So, Carmen, maybe following up on these things, I think we are focusing on the career issues. So you've transitioned from Argentina to US, and then culturally, and of course, it's different cultures. And then how the transition has been, what has been the challenges when we moved from one continent to another continent?
Well, moving to Fort Collins, Colorado to do our PhD was a decision that both, my spouse and I made. And that's the reason why, we ended up in here, and we have stayed in here because both of us are professors in the same department. And so we are far less mobile than others. But in terms of culture, it was a big cultural difference. When we moved to Fort Collins in 1979, this was a very small cowboy town. And we, I had lived all my life in Rosario, in Argentina, which is the second largest city. And then during the last 4 years of our physics diploma, we actually lived in Buenos Aires because we were doing research in two research institutes. I was actually working at the Atomic Energy Commission there. And imagine, this is the difference between being in New York and coming to Fort Collins, where, Fort Collins is a beautiful community. And now it's a very diverse, it's a much more diverse community and much more international. Colorado is beautiful. I mean, I love to live here. It's aesthetically beautiful. The weather is fantastic. But yes, the culture shock was big. And especially because even at that time, the culture shock was big in several aspects. Well, number one, we came into this small town where, to actually get a croissant, we had to go on a Saturday morning to a very special place, okay? But in addition, there was a big change in how I particularly fit in society. I was an educated, person with an undergraduate in physics that was coming to actually work on my PhD, and there were not that many women in physics.
Yes.
I mean, which was completely different than in Argentina. In Argentina, my class were approximately 10 students, and about 4 were women. And I came to, CSU, and that year we were 2 women in a group of about 15 graduate students. That was quite a shock, okay? There was also quite a shock in the way that the students interacted. We in Argentina got together we studied in very different ways, in a much more collaborative way. We would get together in the library at the university and solve problems together. You know, I remember clearly when it got the time to prepare for our qualifier, I proposed to the graduate students group to actually hold group meetings and solve problems and discuss problems together. Oh my gosh, that was seen like I wanted to cheat. And so that was quite a cultural shock. But I had a great time during my graduate education. My advisor was English. And just to give you an idea, during the time that I was doing the PhD with him, the Malvinas or Falkland War broke up. Okay, so we had very interesting discussions. But I shared with my advisor the passion for music, and so we had a great interaction. And I learned a lot from him. And again, I learned a lot also from those you know, with whom I work in the department after I became a professor. And I have to tell you, both of us, my spouse and us, have had a fantastic opportunity here at Colorado State University.
Oh, good. Thank you. And so maybe let me ask you the last question because we are running out of time. So you're a great source of inspiration for many people, particularly young women, particularly also people from the developing countries. And so really, what advice you would like to give to young people when they're really starting their careers now, and then what are the things which they should do in order to be able to be successful like you?
The advice that I would like to give everyone, I think that Jean is an example, is work, you know, try to interact with the community and to work at a very young, you know, stage in the development of your professional career. Work with others and work with others that are doing very exciting work and that are also well known in the field, because that builds up then in both, you know, in what you learn, how in what you technically advance, and also in giving you the connections to then move to the next stage. I also feel that you know, that it is important that whenever, you know, and I give this advice to all of the students, the undergraduate students that are, you know, trying to decide whether or not to go for graduate school. I tell them to look, when they look for a graduate school, I tell them to look for individuals with whom that are known to work very well with young professionals. This is very important because those of us who are now mature and that we are in leadership positions need to be aware that we need to give opportunities to young professionals. And these opportunities are in the form of, you know, deciding, okay, you know, this time is your, you know, you will say to your postdoc or researcher in the lab, you give the invited talk. I mean, I don't need to give this invited talk. This is your opportunity, or likewise to write a review paper. It is important to look for individuals that will be open, that you know are working very well and are supporting the professional development of young professionals.
Okay, thank you very much, Carmen, for that wonderful advice and also great talk, and also really answering our wonderful questions about the career and how to manage the work-life balance and then how to really progress in life. And we really want to sincerely thank you on behalf of the IconX, and then we would like to present to you the certificate of you presenting this talk at this IconX Talks. And then obviously, if you would have been in person, we would have been able to present this one to you. And then we will make sure that whenever we meet, and then we'll present this certificate to you. Thanks again for your inspirational talk and your inspirational life and inspirational career. And you've been a wonderful role model for all of us, and particularly for young people. With that, and I think I think Professor Alice Chang has already mentioned to you about IEEE NEMS conference next week, and we hope to see you next week. And then, of course, next Friday, we have, again, our another ICONX talk. And so we look forward to seeing all of you at that time. Okay, thank you, and bye-bye.
Bye-bye. Thank you.
Bye.
Yeah,
Thank you.
bye.
Bye.
Yeah, cover.